We've already seen what happens when we have a pulse going one way get superimposed with a pulse going the other way. But let's see what happens when we have a continuous wave going to the right interacting with a continuous wave going to the left. So here we have a wave going to the right. It's just a sinusoid and it's traveling along, and it has a certain speed, which is the frequency times the wavelength. And if the frequency is higher, then if we sit at one point, then things go faster, and that means that because the wavelength hasn't changed, it means the whole thing is traveling quicker. Equivalently, if we make the wavelength bigger, then we can see it's getting longer on this axis, and indeed the actual peaks are moving faster again. If I want to change the direction of the motion of travel of that wave, all I have to do is put in one minus sign into my equation, and there it goes, going backwards. Now the question is, what happens if I have one of these going to the left with a particular frequency, plus one of those going to the right with exactly the same frequency? So the best way to visualize two sine waves passing through each other is to see two pulses going through each other and then make the pulses wider and wider until they just cover all space. So there's two pulses, they pass straight through. Let's start that again, except this time we'll make them wider. And you can see when they pass through, you get that sort of pulsing interference pattern for longer. And in the limit where they're infinitely wide, so we make them super, super, super wide, then you just get pulsing and nothing else. And if we slow that down, I'll just slow that down, you can see that what you're getting there is an interference pattern that's going up and down. If you sit at any point, you can see that those peaks are not traveling left or right, they're standing still. And this is called a standing wave. And these points here, where the standing wave is moving a lot, are called antinodes. And these points here, where it's not moving at all, are called nodes. So here's our standing wave, where both the frequencies are the same. Now what happens when we make the frequency of the wave moving to the right a little bit higher than the frequency of the wave moving to the left? Let's do that. And what we see is we still kind of have a standing wave, except now we can see that it's moving. And so the nodes are moving and the antinodes are moving. So it's still oscillating, but now the nodes are moving. And if we change the frequencies so that the frequency of the wave to the left is a higher frequency, we can see that the antinodes and the nodes are all moving to the left. So if you want a proper standing wave, you've got to organize for the frequency for a wave going one way to be exactly equal to the frequency for the wave coming the other way. And the best way to organize that is to have it reflect off something. For example, you might have a string, and if the string has a fixed point at one end and a fixed point at the other end, then if I induce some kind of wave here, it's going to travel along and bounce and come back. And so the frequency going in each direction is going to be the same, and what that means is I'm going to end up with a standing wave, naturally here. Now if I pluck a guitar string, I'm going to get a very specific kind of standing wave. A particular one. And the reason for that is I have to have a standing wave that has to have a node at the end. At each end, in fact. And there are only certain wavelengths of wave that can have a node at each end.